Good morning, everyone. I am honored to represent the joint team from the University of Hong Kong and ByteDance Seed to present our latest research, Temporal Equilibrium Mean Flow, or TEMF. While mean flow has emerged as a powerful framework capable of training few-step generative models from scratch without distillation, it hits a severe bottleneck when scaling up model capacity, a phenomenon we term the scale gap. Today, I will delve into the mathematical root of this degradation and demonstrate how our proposed temporal equilibrium and dynamic boundary scheduling mechanisms elegantly resolve it, setting a new state-of-the-art for one-step generation on ImageNet 256 by 256.
Our motivation stems from a highly counterintuitive observation. Please direct your attention to these three plots showing the FID progression across M, L, and XL model scales. The ratio in the legend refers to the proportion of trajectory samples. Two critical issues immediately stand out. First, extreme sensitivity to this sampling ratio. A simple shift in this hyperparameter drastically alters the final FID. Second, and more importantly, larger models suffer more severe collapse. In the XL model, setting the ratio to 70% causes the FID to explode past 250. This reveals that vanilla mean flow cannot stably optimize with a high proportion of trajectory samples. The deeper the network, the worse the instability, effectively breaking the scaling law for one-step models.
This scatter plot provides a macroscopic view of the landscape. The x-axis represents training compute, and the y-axis is the one-step FID. As you can see, existing methods like Shortcut XL, ICT-XL, and IMM-XL either suffer from suboptimal FIDs or demand exorbitant compute. While vanilla mean flow is viable at the base scale, it stalls at the XL level. In contrast, our TEMF family, the blue and purple clusters, not only pushes the FID significantly lower at equivalent compute budgets, but also exhibits a beautiful monotonic scaling trend. How did we bridge this gap? The upcoming mathematical analysis will reveal our solution.
Before diving into our solution, let's briefly review the mean flow mechanics. Mean flow introduces an average velocity field. Through differential calculus, this yields an elegant identity. The average velocity equals the instantaneous velocity minus the time interval scaled by the total derivative of the average velocity. Based on this, original mean flow formulates the objective, regressing the network against the stop gradient target. While theoretically sound, calculating gradients for this objective hides a massive variance trap, which is the exact culprit behind the model collapses we saw earlier. This brings us to the theoretical core of our paper. We rigorously analyzed the gradient variance of the mean flow objective. Let the time interval be delta. According to our Theorem 1, temporal variance imbalance, the gradient variance bound is dominated by two conflicting terms. The first explodes as delta approaches zero near the boundaries, growing rapidly due to path curvature. The second dominates for large delta, where the Jacobian vector product term's variance takes over. This creates an irreconcilable tension. Short intervals demand aggressive constraints, while long intervals suffer from variance explosion. Vanilla mean flow uses a uniform unweighted loss, which inevitably tears apart the optimization dynamics in deep, large-scale networks. Having diagnosed the issue, we introduce our first remedy, temporal equilibrium weighting. Our goal is to keep the gradient variance constant across all timescales. By solving the variance equation, we derive the ideal weighting function. In practice, we parameterize this, so the first term balances the boundary constraints for short intervals, while the second term suppresses amplification for long intervals. Our Theorem 2 rigorously proves that with this weighting, the gradient variance of TEMF is uniformly bounded by a finite constant across all time steps. This fundamentally stabilizes the training foundation for large-scale models. Beyond loss weighting, we must also overhaul the sampling strategy, our second remedy, dynamic boundary scheduling. We define the boundary constraint strength. Following our Theorem 3 and the analysis of the bias-variance trade-off, the optimal constraint strength should decay exponentially as training progresses. In plain terms, during early training, the model hasn't even learned the endpoints, so we enforce heavy boundary sampling to stabilize them. Once somewhat converged, we use a sigmoid schedule to ramp up long interval trajectory samples, forcing the model to learn precise global trajectories. This smooth two-stage transition eliminates the remaining risks of training collapse.
For state-of-the-art image quality, classifier-free guidance is mandatory. In TEMF, we directly learn the CFG guided velocity field. However, directly fitting this introduces massive variance because the guidance scale is typically large. To counter this, we improved the velocity mixing mechanism. We decay the mixing ratio from 0.3 down to 0.1 as training progresses. This ensures early stage stability while releasing the full power of CFG in the late stages, allowing our model to output CFG-enhanced images natively in a true single one-step.
Do these mathematical designs actually work? Let's look at the rigorous ablation studies in Table 1. In Table 1A, with no weighting, FID sits at 6.52. Suppressing only JVP, or only the boundary, helps partially, but only the full weighting drops the FID to 4.31. Table 1B empirically validates our Theorem 3. The exponential dynamic scheduling outperforms other static or linear schedules. Table 1D shows the incremental gains. Starting from a baseline of 6.17, adding temporal weighting reduces it to 5.26. Dynamic boundary brings it to 4.93, and CFG integration finalizes it at 4.31. This proves every component is essential and complementary. The remaining tables confirm the robustness of our hyperparameters.
This brings us to our proudest results, evaluated on the highly competitive ImageNet 256 by 256 benchmark. Among all few-step consistency models, our TEMF-XL achieves a 1 NFE FID of 2.81, and with slightly more training, it reaches an astonishing 2.62. This completely obliterates vanilla mean flow, ICT, shortcut, and IMM, and even beats many massive autoregressive models. Furthermore, given a mere two-step budget, our FID drops to 2.30. This matches or outperforms heavyweights like DITXL, which require hundreds of evaluations. Table 3 shows that on unconditional CFAR 10, we achieve the best FID of 2.81 without any preconditioning. This proves TEMF is a fundamental, universally applicable architectural breakthrough.
Please enjoy these uncurated ImageNet images, all generated in a single step by TEMF. Here we display the outputs from our M and L scale models. Pay attention to the high-frequency details, the fur textures, the sharp geometric edges of architecture, and the complex lighting reflections. This slide showcases the outputs from our XL model. Traditional one-step models usually suffer from oversmoothing or structural artifacts. Because TEMF enforces temporal equilibrium, the model learns the straightest possible transport flow, perfectly preserving these details. Below is our algorithm 1. Notice that despite our rigorous mathematical derivations, the actual implementation is incredibly clean and highly deployable within existing flow matching ecosystems. To wrap up, let me summarize our contributions in 3 key takeaways. We identified and mathematically formalized the temporal scale imbalance, proving it is the root cause of large-scale training collapse in one-step generation. We proposed the TEMF framework, curing this issue using 2 precise mechanisms: temporal equilibrium weighting and dynamic boundary scheduling. We established a new state-of-the-art of 2.62 FID on ImageNet 256 by 256 for one-step synthesis. Bridging the scale gap is just the beginning. We believe TEMF paves the way for truly real-time, physically accurate video and 3D generation models in the near future. Thank you for your attention. I am Yuan Peng Tu, and I'm now happy to take any questions.